I am Dr. Kalyan Raj, Professor of Chemistry. The recent curriculum design in Visvesvaraya Technological University for the Applied Chemistry course in the Engineering Chemistry, one of the unit that is with the title Materials for Memory Devices and Display System. Materials play a very important role in engineering applications, and in particular the chemistry materials of chemistry much more advanced in the technology. So coming to the topic with the memory device and display system, so we have memory device. To start with, example, a chip, a computer chip, a CD, a DVD, a USB or external hard disk, what we say pocket hard disk, even for our desktop or even laptop. So they are all considered as a memory device. So how we can define the memory device is, a memory device is a piece of hardware made up of semiconducting materials used to store data. So all these are CD, DVDs, USB, they all become the example for memory device. So coming to the major broad classification of memory devices, we have four different major classification. The first one is transition type electronic memory, and second one is capacitor type electronic memory, and third is resistor type electronic memory, and fourth one is charge transfer electronic memory. One is transistor type electronic memory. So in the transistor type electronic memory, a transistor is a miniature electronic component that can work either an amplifier or a switch. So here billions of transistors of working to become a switch, which can be switched in the form of on or off. Each transistor can be different states and stores of different kinds of numbers, particularly 0 and 1. Since chip can make billions of such transistors, every number and letter can stored in the form of 0 and 1. Coming to the second type of electronic memory, that is capacitor type electronic memory. So in the capacitor type electronic memory, as we are all aware in the physics capacitor, a capacitor is consisted of two metal plates which are capable of storing charge. It is like a battery that holds data based on energy. If the capacitor is charged, it holds the binary numbers, again 1 and holds 0, when a cell is discharged. So the diagrams of the capacitor type memory we can see from this capacitor type of that parallel plate capacitor, as we are aware. So next, coming to the third type of memory, electronic memory in particular, that is resistor type electronic memory. So in this resistor type electronic memory, memory device consisting of switchable resistive materials, as already mentioned, material play a very important role here also. Switchable materials are classified as a resistor type memory or resistive random access memory, that is RRAM. So a resistor type electronic memory usually has a simple structure having a metal insulator metal. We have a metal insulator and metal. Structure generally referred as MIM, metal insulator metal MIM structure. The structure comprises, as we are aware here, the structure comprises an insulating layer and sandwiched between two metal M electrodes and supported on a substrate of materials like glass, even silicon wafer and plastic and metal foil, like that. The device is under high resistance state or off and logically again zero state when the resistance is charged, charge transfer effects. So here in this transfer effects memory device is a special way. There is charge transfer, it is also called CT. Memory device is a complex defined as an electron donor acceptor. As we are aware in complex in the coordination chemistry, we are familiar in earlier chemistry coordination compounds, we say donor and acceptor like that. We say donor as D and A as a complex characterized by an electronic transition. It is purely a transition electronic excited state in which a partial transfer of charge occurs. That donor moiety to the acceptor moiety donates. The conductivity of a charge transfer complex is shown with this diagram. So how electron donates and electrons is going to accept. So with this continuation we have a concept called LUMO and HOMO that is there. It is clearly is given, that's what LUMO and HOMO, that different way of excitation of the electrons in the intermediate states of the energy, that is lower and higher state, that is explained with the charge transfer, and these are the flow charts and ideas are given how the electron excitation with lower to higher, it is clearly explained that. So next we are going for the organic memory device by taking P type and N type semiconducting materials. So the other in detail. Coming to the classification of electronic memory, we have non-volatile and volatile types. See here the volatile means whenever there is no power in continuation, this type of memory will erase it out, and non-volatile type, even though there is no power source, we are going to connect the device, they will the memory will going to retain. So under the classification of non-volatile we have ROM, read only memory, and also hybrid. In the read only type memory we have WORM, write once and read many times one, and we have EPROM, that is erasably programmable read only memory under the classification of hybrid. We have flash and EEPROM, that is ROM stands as usual with read only memory, that EEPROM electronically erasable program that is what the further classified as. Coming to RAM, we have DRAM and SRAM subclassified. This is what this stands, this RAM, that is dynamic, and what SRAM stands here, it is that is static. That is how the different memories are classified, and we are taken that particular application in our devices. Coming to the history of memory devices, how the history starts in the memory device research and application like this. In the year 1968, the memory device material starts from lead and polydivinyl benzene, lead bistable electrical switching device as an information storage device to start, continues from 1968, again in 1969 tyrosine films sandwiched between metal electrodes are play important role as a memory device material. In the year 1970, the memory device comes in the form of thiocyanines and polystyrene bistable switching materials, and continues with so many advances with this kind of material. And coming to this recent trend, organic based materials in the form of memory materials, and expected with biodegradable memory devices also in the coming days in the memory device materials for the application of computer. We discussed different categories of electronic memory devices. We have organic memory devices also. Organic molecules also play important role as a memory device. Coming to that, first type, we say P-type organic semiconductor materials. We have taken an example, pentacene, which we are shown in the diagram in the form of a structure with 5 fused benzene rings. An organic molecule with a pi conjugated system possess holes as major charge carriers is called P-type semiconductor. So coming to the principle involved with this organic semiconductor, particularly P-type, when a positive voltage was applied between gate and source, it was found no flow of electrons to drain due to higher energy gap between the Fermi level of gold as a source. We have a concept of LUMO of pentacene. On the other hand, when a negative voltage is applied between the drain and source, holes are induced to the source. So I am showing here the left schematic ideas where we have an energy of LUMO and HOMO system when we works with the principle of P-type organic memory device. This permits a channel of charge, particularly charges in particular holes, to drain through semiconductor and interior interface when a secondary voltage is applied. Therefore, it is called P-type semiconductor. Yes, coming to the organic memory device with the second type of N-type organic semiconductor materials. As we discussed in the previous P-type, we have pentacene, we have in the ring structure of fused benzene form. If you observe that the all hydrogen which is connected to this ring, now it is replaced to fluorine. Once if it is hydrogen replaced to fluorine, we are all aware in the earlier chemistry basics, fluorine is an high electronegative material. So with this N-type semiconducting material of perfluoropentacene, an organic molecule with again pi conjugate system with electron withdrawing substituent groups and possess electron as a major charge carrier. That is how it becomes an N-type semiconductor. In pentacene, when hydrogen atoms are substituted, what we are already observed, by highly electronegative fluorine atoms, it is called perfluoropentacene. What we are seeing, all the hydrogen is replaced with fluorine and acts as a N-type semiconductor. This becomes an N-type semiconductor. Here, the principle of working this, when a positive voltage is applied between the source and drain, electrons are induced into the source of gold. This permits the channel of charges to drain through a semiconductor insulator interface as the band gap between Fermi level of gold source. Their LUMO energy perfluoropentacene, we have a value of 1.95 electron volts, which is lower than LUMO energy of pentacene. Therefore, it is become an N-type semiconductor. See, coming to the display systems, a display is a device that shows visual information in the form of an image or a video to a particular users. A display system is a collection of hardware and even also software components that work together to generate and to present visual information to the particular users like this. So when we are discussing in the display system, we have to discuss with the photoactive and electroactive organic materials, how they play important role. Photoactive organic materials finds organic polymers. They can absorb light and convert into electrical energy. Electroactive organic materials are also materials that can undergo reversible electrochemical reaction and store or even release electrical energy. So these materials contains conjugated double bond that allow the efficient absorption of light in the visible near infrared range and electromagnetic system. So here is the diagram. We can show the working principle of photovoltaic applications. So in photoactive electroactive materials, particularly we are taken example OLED, organic light emitting diodes, as a display system. Here a layer of photoactive and electroactive material is sandwiched between two electrodes. What we are shown in the diagram, it is sandwiched in two electrodes, with one electrode being transparent to allow for light extraction. Another is there with sandwiched form. When a voltage is applied across the electrodes, generally we will apply the voltage across the electrodes, the material absorbs the photons and generates electron volt pair, which can be transported through a material by a built-in potential or even external electric field. In the next step, there continuation with that diagram what we shown here. In the light emitting layer of an OLED, that particularly expanded as organic light emitting diode, the recombination of energy of electrons from the cathode and holes from the anode excites the material, causing it to emit light when returning to the ground state. The transported electrode allows for the extraction of emitted light from the light emitting layer, resulting in a display that generates its own light. So this is about the application of OLEDs and how the working principle. Coming to the one more concept of this display system in the form of optoelectronics. So optoelectronics is a very interesting branch of electronics that deals with an interaction between light in the form of an optical and electric fields in the electronic form. So coming to optoelectronic devices are electronic devices that are capable of emitting, detecting or manipulating light. Example of such device includes our familiar LEDs, light emitting diodes, photodiodes, solar cells and even optical fibers. Coming to the working principle of this optoelectronic device, in optoelectronic devices such as photodiodes, when a photon with energy greater than the band gap, whatever we say the band gap, energy of the semiconductor materials is incident on the device, it is absorbed by the semiconductor material, creating again an electron volt pair. The electron is excited from the valence band to the conduction band, where it is free to move and can be collected as electrical current. So when optoelectronics application all there, nanomaterials are play very important in this display system, and particularly because of the special properties of silicon nanocrystals in optoelectronics. Silicon nanocrystals exhibit strong quantum confinement. That is the most important property, strong quantum confinement effect due to their small size. And silicon nanocrystals are high photoluminescence quantum yield, which makes the attractive for the application in light emitting devices. Silicon nanocrystals are even biocompatible and can be easily integrated into biological systems for bioimaging and also biosensing applications. And one more important application of silicon nanocrystals, they are non-toxic and biocompatible and making them safe for the use in medical applications. So, if you take one such example in this particular advantages, we have polythiophene P3HT used in optoelectronic device. So, this is how the 5-membered ring connected with the heterosulfur that becomes the polythiophene we mentioned as P3HT. It is poly 3-ethyl thiophene or even P3HT we call, is one of the most studied, what we are shown structure here, most studied and widely used polythiophenes due to the desirable properties such as high charge carrier mobility, high absorption coefficient in the visible region, and good solubility in common organic solvents. That is the one important application. Next, P3HT has a greater capability as a high absorbing material in organic electronic devices. P3HT has a crystalline structure and good charge transport properties required for optoelectronics. P3HT has a direct allowed optical transition with fundamental energy gap of 2.14 electron volts. The fundamental band gap of P3HT is in the visible range of 490 nanometer, corresponding to pi to pi star transition, giving in electron volt pairs. P3HT indicates that increase in the conductivity is associated with increase in the degree of crystallinity. That's what the P3HT molecule, what we are shown here. So, coming to the applications of P3HT, it is used to fabricate organic field effect transistors, one of the most useful devices in the electronic field. It is mentioned as OFETs, used as a volt transporting layer in organic light emitting diodes in OLEDs to improve their efficiency and stability. P3HT composite application in energy storage sensing and catalysis. P3HT can also be used in the fabrication of most useful biosensors, even in the manufacture of small windows, particularly smart windows in the electronic device, they are going to use with that. Materials called PVK, that is poly-9-vinyl carbazole, it is abbreviated as PVK. This structure shows how the fused ring is connected with the heteronitrogen, and it is mentioned as PVK as a processable polymer that has been widely used as a volt transport material called HTM in a planar heterojunction perovskite solar cells. PVK, the structure what we mentioned here, PVK has a high gloss transition temperature TG value, which ensures the thermal stability of the solar cell. Coming to the properties of this PVK, luminescence. Luminescence is the property when excited with light or an electric field that PVK emits light in the blue violet range of the visible spectrum, and also processability of PVK is highly processable polymer that can be easily spin coated or even printed to form thin films for the use of optoelectronics devices. Solubility wise, PVK is soluble in wide range of solvents, which makes it easy to prepare solution in the polymer processing. Thermal stability wise, PVK has a high gloss transition temperature, which means that it can withstand with high temperature without degrading. Coming to the applications of PVK, it is used as a resistive material, particularly electron beam and X-ray lithography. PVK is used in the fabrication of light emitting diodes and even laser printers. PVK is used in the fabrication of organic solar cells when combined with titanium dioxide on a glass substrate. PVK is used in the fabrication of solar cells when combined with perovskite materials. PVK perovskite junctions are used in the fabrication of highly efficient and stable planar heterojunction perovskite solar cells. So that's an important application of PVK. We have state of matter classified in the form of solid, liquid, gaseous, or even the fourth state called plasma state. With that respect to coming to a new class of matter referred to as liquid crystals. So they have a special property characterized, even though they are crystal form of a solid, a moving property of the liquid in combination, they are become a liquid crystal. So liquid crystals are also referred to as a moving solids. So liquid crystals are state of matter that has properties of both liquids and crystals. They are characterized by having an ordered molecular arrangements like a crystal, but the ability to flow like a liquid. This unique property play a very important role and ideal for use in various applications, such as very familiar system called liquid crystal display system. See, coming to the classification of liquid crystals are broadly classified in the form of thermotropic. They are temperature dependent. Under the subclass of the thermotropic, we have nematic liquid crystals, smectic liquid crystal, cholesteric liquid crystals, and also discotic liquid crystals. And one more classification under the liquid crystal called lyotropic, concentration dependent. Coming to one by one properties of the thermotropic liquid crystals, the nematic liquid crystals. In nematic liquid crystals, molecules are oriented along a common axis as we shown in the diagram, but they are free to rotate around it. This results in a fluid-like appearance, and they are commonly used in LCDs, liquid crystal displays. Nematic liquid crystals can be classified into uniaxial or even biaxial nematic based on their orientation under an external field. So coming to the smectic subclass of liquid crystal under thermotropic, temperature dependent. In smectic liquid crystals, the molecules from layers with their long axes aligned parallel to one another. The layers can be further classified into subtypes such as smectic A and smectic B, as we shown in the diagrams, and based on the arrangement of the molecules within each layer. The third subclass of the thermotropic liquid crystal called cholesteric liquid crystals. In the cholesteric liquid crystals, the molecules are arranged in a helical structure, as we shown here in the diagram. Helical structure giving them unique optical properties. They are often used in optical applications such as light filters and also even reflectors. The fourth subclass of the thermotropic liquid crystal called discotic liquid crystal. Coming to the working of LCD, that is liquid crystal display, as we are aware, liquid crystal find a very important role in display system, and the arrangement of this working of LCDs as shown here. A layer of liquid crystal material is sandwiched between two glass substrates. The glass substrates are transparent and thin, which are coated with a layer of transparent electrodes. Another side of the first glass substrate is coated with indium tin oxide, that is ITO, and second glass substrate coated with color filter. A thin alignment layer made up of polymer is applied to the electrode layer to align the liquid crystal molecules. A backlight is positioned behind the LCD panel to provide illumination. So coming to the working of LCD, the backlight provides illumination of LCD panel. When no voltage is applied to the liquid crystal layer, the liquid crystal molecules are randomly oriented. When a voltage is applied to the electrodes, it creates an electric field that causes liquid crystal molecules to align with the field. The amount of voltage applied to the electrodes determines the degree of alignment of the liquid crystal molecules and thus controls the amount of polarization of light passing through the liquid crystal layer. The light passes through the liquid crystal layer and reaches the color filter layer. The filters allow only specific colors of light to the subpixels, creating a full color image. Coming to the properties of liquid crystals, anisotropy. Liquid crystal exhibits anisotropy, which means that their properties depend on the direction in which they are measured. The second property called optical properties. Liquid crystals have unique optical properties including fibrinousness, which makes them useful in displays and other optical applications. Polarizability. Liquid crystals are polarizable, which means that they can respond to an electric field. Viscosity as the fourth property. Liquid crystals have relatively high viscosity, which makes them resistant to flow. Coming to the phase transition. Liquid crystals undergo phase transition, different ordered states. This leads to the change in optical properties. And finally, coming to the chemical stability, liquid crystals are generally chemically stable, which makes them suitable for use in varieties of applications. Coming to the applications of liquid crystals displays that place in consumer electronics and computers applications. Temperature sensors and thermometers, they find application in optical shutters and filters. They find application in electro-optic modulators in telecommunications. They find application in optical data storage and holography. Liquid crystal plays a very important role as an application way in alignment layers in LCD manufacturing and widely applicable to the biosensor design and bioimaging in medical applications. So, in the emerging technologies in the display system, organic light emitting diodes, OLEDs, play a very important role in the television and electronic device, particularly in the display application. Coming to the principle and working of organic light emitting diodes, referred as OLED. Organic light emitting diode is a carrier injection type electroluminescent device that uses organic materials. The emission mechanism of the OLED is similar to inorganic LED, light emitting diode, which is inorganic LED what it is there, but an organic version incorporated here, therefore it is called as OLED. OLED device consists of two electrodes. As we shown in this diagram, OLED consists of two electrodes, an anode and a cathode, and an organic layers are placed. An organic layer is placed between anode and cathode. Multiple organic layers are used. There is an option to change the different organic layers, organic materials. Each layer plays an intrinsic role. When a voltage is applied to an OLED device, when we applied a voltage to an OLED device through an anode and cathode, charge carriers are injected in the form of electrodes to the organic layer. Anode injects holes, positive charge, and cathode injects electron, negative charges, to the system. The holes and electrons are transported to an emission site and recombined. Organic materials in the emission sites are excited by recombination of holes. when this recombination of holes and electrons occur, when the excited organic material returns to its ground state, then emission occurs. So the complete schematic diagram of this construction of OLED is shown. Coming to the properties of OLEDs, OLED, as I already mentioned, coming to the electronic device, new TVs and electronic display ways, they have a unique properties. High color saturation. OLED display can produce very saturated and vivid colors, making them ideal for application where color accuracy is important. And deep block levels. OLED gives those a very high contrast ratio. That's color pixels, images and videos look more lifelike. Wide viewing angle. OLED display images and videos be viewed from almost any angle without distortion or even color shift. Low power consumption, it is also very important, consumes less power than the other display technologies, making them more energy efficient and long lasting. And thin and flexible form factor. So foldable displays and all very way consumes less power, other display technologies making more energy efficient and long lasting. Thin and flexible form of factors for a use of curved display. We are all seen recently, even if we have a monitor, a TV, display system, they comes in the curved display form. They are called coming to flexible display. Wearable devices we can wear to our hand in the form of digital watches like that. Fast response time. OLED display a very fast response time, which makes them ideal for use in application where motion blur it is concerned, such as gaming and virtual reality. So coming to the one more technologies added to this OLED called quantum light emitting diodes. Referred as QOLEDs. QLEDs. The principle of working of QD LED, or it is quantum dot LED, QLED commonly called, they are form light emitting technology for creating a large area displays that could have application for TVs, cell phones, digital cameras. QD LEDs are going to be the next generation display technology. I mentioned already, in the coming generation, in the later stages, there is a lot of changes in the display system. After OLED displays, the structure of QD LED, quantum dot, or even quantum light emitting diodes, similar to the fundamental design of OLED, but the difference is the light emitting is from the QDs, quantum dots, such as interesting chemical substance like cadmium selenide, CDSE, nanocrystals. The nano play important role here. A QD LED, the construction and working of a QD LED device, as we shown in this diagram, a QD LED device consists of two electrodes. As usual, an anode and a cathode and a QD layer. Instead of just organic layer, we have quantum dot layer, which is specialized nanomaterial kind, placed between two electrodes. When a voltage is applied to an QD LED device through anode and cathode, charge carriers are injected from the electrodes to the QD layer. They have organic layer in the previous OLED. Here to the QD layer, anode injects holes, positive charges, and cathode injects electrons, negative charges, to the system. The holes and electrons are transported to an emission site and recombined. QD material in the emission site is excited by recombination of holes and electrons. When the excited QD returns to its ground state, that emits photons. In QD LED, what we shown in the diagram, for better recombination efficiency, a single layer QD is in colloidal form as an emissive layer. They are taken in the form of that in this construction. So, coming to the properties of this QD LEDs or even quantum light emitting diodes, wide viewing angles, which means that the colors and image quality remains consistent even when viewed from different angles. Very interesting property it is. Environment friendly. QLEDs are free from harmful substances such as mercury and lead, making them more environment friendly and traditional LCD displays. Accurate and vibrant colors. QLEDs use quantum dots as material in the form of a quantum dots to emit light of a specific color when excited by a light source or electric current, resulting in highly accurate and vibrant colors. So, coming to the energy efficient, QLEDs are more energy efficient than traditional LCD. What we have traditional LCD called liquid crystal display, because they require less backlighting. High contrast. QLED display have high contrast ratios, which means that the difference between the darkest and brightest areas of the display is greater, resulting in more detailed and lifelike images. Long lifespan. This is also a very, very important property. QLEDs have a longer lifespan. Traditional LCD display than traditional display, because they do not suffer from same issues of backlight burnout or color fading over time. Fast response times, that they can display fast moving images without motion blur or even ghosting. Flexibility, what we say flexible display in the recent days, OLEDs can made on flexible substrates, allowing for the creation of flexible display that can be bent or even curved. That is called bent, curved display systems are coming in the market in form of that. Coming to the applications of quantum light emitting diodes, QLEDs, used in ultra fast and energy efficient communication system, and QLEDs can be utilized in quantum photography to secure communication channels. Additionally, QLEDs can be employed in medical imaging applications such as MRI machines to generate high resolution and accurate images. They play a very important role in medicinal fields. QLED can be used in quantum computing. Very interesting. Quantum computing as a source of qubits for information processing. QLEDs can be utilized in quantum sensing applications for high precision measurements. Televisions and displays. QLED displays are commonly used in televisions, monitors, smartphones and other electronic devices. QLED display can be used in advertising displays such as digital billboards and signage. So these are the applications of QLEDs.